Welcome to a quick refresher course on symmetry and intercepts. I suggest you grab your notebook for next year, take some good notes, and feel free to pause and rewind whenever you need to. So our goal today is to review symmetry. Now it might sound very trivial to you, something you've probably talked about since kindergarten. You can imagine taking a piece of paper when you were in kindergarten, you folded it in half and you cut out a heart, and when you opened that heart up, it became symmetric to an axis. Okay, you had the same thing on both sides. And that's all we're talking about with symmetry. Now, in this case, you can be symmetric to the y-axis, to the x-axis, and to the origin. And we have some little algebra techniques we can use to test for symmetry. So, to test for symmetry, it's very simple. It's basically one rule with different outcomes. So first and foremost, let me start with even symmetry. Okay, a function is said to have even symmetry if it follows this rule. F of negative x equals f of x. All right, and back to function notation, basically you're going to substitute negative x in, and you want to get out f of x. And I'll go through some examples step by step in a moment. But let's go ahead and jot that down. So even symmetry, here's our rule. Now, even symmetry applies, you are symmetric to the y-axis. Okay, so maybe you can think of a function that is symmetric to the y-axis that's even. Probably the easiest function is y equals x squared. If I were to sketch y equals x squared, I think you could easily see that it's symmetric to the y-axis. Okay, this is called an even function. Now, something special to take note. What's special about the squared exponent? What type of number is it? Well, in fact, it's even, and that's part of what makes it an even function, is that it has an even exponent. And again, it's symmetric to the y-axis. The second type of symmetry you can have is odd symmetry. Okay, and odd symmetry is going to follow a very similar rule. F of negative x, so notice they start the same, but this is equal to negative f of x. So basically, I need the negated version of my function. Now, what is that symmetric to? Well, it's kind of easy to remember. Odd is symmetric to the origin. And I think those O's should stick out for you. The odd function is symmetric to the origin. Now, can you think of an easy odd function? Okay, I would say y equals x cubed. All right, think about its exponent. 3 is clearly an odd number, not an even number. If I take a look at x cubed, remember it's concave down till it gets to the origin, and then it's concave up. Now, what's special about an odd function in respect to the origin is basically if you can flip this 180 degrees and see the same picture, then you know you have an odd function. All right, so again, if I were to take this picture and flip it upside down, it should look the exact same. And that's how I test visually if my function's odd. Okay, it should look the same 180 degrees upside down. Now, a function doesn't have to have symmetry at all. For example, this function is clearly not symmetric to the y-axis. If I fold it in half here, it's not going to land on top of each other. It's not symmetric to the x-axis. If I fold it over the x, it's not going to land on top of each other. And if I flip this picture upside down, I don't get the exact same thing. So we like the word neither. It has neither even or odd symmetry, and that's okay. Not all functions have to have even or odd symmetry. In our next example, our goal is to determine whether we have even, odd, or neither type of symmetry. So all we're going to do is follow the rules. So let me recall those two rules. Even is symmetric to the y-axis, and when I substitute negative x, I get the original function out. Odd is symmetric to the origin, match those O's up. When I substitute negative x, I get the negative f of x out. So, to me, the easiest thing to notice is that in either case, you're substituting a negative x, and all you care about is what you get out in the end. So, let's substitute in negative x into our given function. Remember, use parentheses. And our goal is just to determine what do we get out. So when I substituted in negative x squared becomes positive x squared. This becomes negative x plus 2. And all you're doing is comparing this to the original function. Is it the exact same? Well, I would say heck no. This is now a negative x and it was a positive x. That rules out even. It's not the exact same f of x. Did I negate every single term in there? Well, the x squared was positive and it's still positive. So no, I did not negate that term. I did negate the second term and I did not negate the third term. Remember, you have to negate the whole function. So I would say this function has neither type of symmetry. Either it comes out the same, comes out all negative, or it's a neither. Let me give you one more example. All right, example 2. F of x equals x cubed plus 6x. We're going to test for symmetry. So it doesn't matter if I'm testing for even and odd, you're plugging in negative x and determining what you get. So again, based off what you get determines whether you're even or odd. All right, so just take your time. When I substituted in negative x, I'm getting negative x cubed. When cube and negative, it's a negative, minus 6x. All I'm going to do is compare that answer to the f of x function. Is it the exact same? Well, it was positive x cubed and positive 6. Now it's negative x cubed and negative 6x. So I would say, no, it's not the exact same. And is it the complete opposite? Did both signs change? Yes. And since that happened, we would say this function is symmetric to the origin, which implies that it is an odd function. So origin, odd function. So just to recap, when you substitute in negative x, if you get f of x, and I just want to state that's the original function, that implies that you are even, and that is with respect to the x-axis. If you substitute in negative x and you get the negative version out, okay, and I want to be clear, that means all terms have been negated. That implies you are odd, and that is symmetric to the origin. Odd and origin. And again, I can't stress, all functions, all terms have to change signs. All right, let's talk about intercepts. First of all, we'll talk about x-intercepts. That's simply where your graph crosses the x-axis. So let's go ahead and sketch this picture in our notebook here. This graph has 4 x-intercepts, and let's go ahead and circle them. Again, it's just where your graph crosses the x-axis. Now, there's something extremely special about every x-intercept. Okay, all 4 of these points we circled have something in common. Can you think about what that is? What's special at this point, at this point, at this point, and this point? They all share something. Clearly, it's not the x value. Okay, this is pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. Clearly, the x values are different. But what's special, and this is the whole key, is that they all have a y value of, hopefully you've guessed it by now, of 0. And that's what makes x-intercepts special. Every x-intercept has a y value of 0. Likewise, what do you think is special about a y-intercept? Now, we typically only have one y-intercept because if I had 2, I would no longer have a function. You know, for example, if I drew something like this and had 2 y-intercepts, that's no longer a function. That graph does not pass the vertical line test. So it's more practical to have one y-intercept and multiple x-intercepts. So again, this point is very special. Clearly the x value is 0 and the y value could be whatever it wants. So a y-intercept is special because the x value is always equal to 0. Now, keeping those two ideas in mind, that's how we simply find our x and y intercepts. Let's try a few examples. So y equals the quantity x plus 3 squared minus 4. If I want an x-intercept, and if you forget, it's very simple to graph out and just ask yourself what's special about the x-intercepts. Okay, if I want an x-intercept, I know that the y value is equal to 0. So all I simply do is replace 0 into y and solve my problem. Okay, so I've got 0 equals order of operations. I'm just going to FOIL that out. Hopefully you can do that in your head. X squared plus 6x plus 9. If you can't, write it twice in FOIL. Minus 4, so I've got x squared plus 6x plus 5 equals 0. Quickly factor and solve. X plus 5 and x plus 1. Therefore, I have x-intercepts at -5 and -1. So it's very simple for me to get an idea of what this graph looks like. It's going to cross the x-axis at -1 and again at -5. Now, I should know what shape this is making. I see a squared term, so I know I'm going to be making the shape of a parabola. Now, before I actually graph it, I'm going to go ahead and get the y-intercept. And again, if you forget how to find it, just make a quick sketch and ask yourself what's special about a y-intercept. Well, no matter where I cross the y-axis, I'm always going to have an x value of 0. So this time I'm going to substitute 0 into x. I've got 0 plus 3 squared minus 4. So y equals 9 minus 4, which is 5. So I know that this graph is going to cross at y equals 5. So now I have an idea of what this graph looks like. It's an opening upward parabola, hits the x-axis at -1 and -5, and hits the y-axis at 5. Alright, so same idea. Hopefully this equation looks familiar to you. This is called an implicit equation when we have x and y in the equation. So we'll do the same thing. We'll find our x-intercept and our y-intercept. So why don't you pause it, try it on your own, and see if you get the same thing I do. So hopefully you can follow my work. X-intercept means y equals 0. Plug it, if it's the x-intercept, plug 0 into y. Y-intercept, plug 0 into x. I quickly plugged it in, and I've got plus and minus 2 for answers. I'm going to do the same thing finding the y-intercept. So if you haven't done it again, pause it, see what you get. And hopefully you've got the same thing there, y equals 4/3. So again, this is telling me the graph crosses the x-axis at positive -2. So -2 and +2, I cross the x, and I'm only going to hit the y once at 4/3, which is just a little bigger than 1. Alright, in this last example here, we're going to find 3 things. Any x-intercepts, y-intercepts, and we'll test for symmetry, and then we'll show a quick graph of what this function looks like. So x-intercept, okay, and again, if you have trouble, just think about crossing the x-axis. What's special about crossing the x-axis? Well, that's the y value equals 0. So I'm going to substitute 0 into y, so I've got 2 over x squared minus 9. Now, if it helps, you can always put that number over 1, and because there's an equal sign, a quick cross multiply. 0 times anything is 0. Set that equal to 1 times 2. 0 equals 2. Does that make any sense to you? I sure as heck hope not, so that just implies that there are no x-intercepts. This time I want a y-intercept. So again, think about what's special about crossing the y-axis. That means the x value is 0. So I'm going to carefully plug a 0 into x. So I've got 2 over 0 squared minus 9. I would say that's a y value of -2/9. Not pretty, but doable. And lastly, I'm going to test for symmetry. Now I think symmetry is pretty easy. You're just substituting a negative x and you're going to see what you get. So when I substitute in negative x, I've got 2 over -x squared minus 9. So that gets me 2 over, if I square a negative, x squared minus 9. Now compare that to the original function. Are you the same, 100% different, or a mix? I would say that's the exact same. Therefore, that implies that my function is even, which of course is symmetric to the y-axis. Now, I'm going to go ahead and sketch this out, and you should be familiar with this from pre-calc. We will actually talk about this again in class, but I can sketch the few things I do know. I know it has no x-intercepts. That means this graph cannot touch this x-axis. And I do know that it crosses the y-axis once at -2/9. So I'm going to stick that there. I'm going to pretend that's -1. I know it's going to hit the y-axis once there. And I know it's even, so it's symmetric to the y-axis, so I should be able to fold it over on that line there. Now, it looks like I don't have much of a graph. This is a little scary. Well, think about this. We know how to find vertical asymptotes. We said set the denominator equal to 0, so if I set x squared minus 9 equal to 0, I think you can factor, you get plus and minus 3. So I know at 3 I have a vertical asymptote, and at -3 I have a vertical asymptote. So you can kind of see how it's symmetric to the y at the moment. Now, what does that tell me about my function? Well, since this point is below the x-axis, remember, you don't have an x-intercept. You can't go up because you can't cross the x-axis. That's telling me that this is looking like this. Again, I can't touch the x-axis and I gotta hug those asymptotes. Okay, again, I also know I'm symmetric to the y-axis. Now, I most likely have something going on outside of this value. So all I'm going to do is I'm going to take 4 and I'm going to plug it in to see where I'm sitting. So I'm going to take my function 2 over 4 squared is 16 minus 9. So I would say that's a value of 2/7, which tells me at 4 I have to plot the point 2/7, which implies that I'm sitting up here. And if I were to plug in -4, I would get 2/7 again because I'm symmetric. And lastly, I can quickly check for any horizontal asymptotes. I can do a quick power fight, circle my biggest powers. That's a small over large, which tells me I'm at y equals 0. So I'm going to throw in my asymptote here. And that tells me that this graph is sitting, between here, those asymptotes, and here. And again, this graph should look symmetric. So this is what we'll be leading into when we get probably to the second day of school, back in class there. So again, if you have any questions, don't hesitate, but take your time, replay what you need to, and I look forward to seeing your assignments.